Welcome, everyone.
Well, that's exactly right. Welcome to the very last session of the day. And it's a repeat of a very fine one, too, by the way. It's the use of IR cameras to track the health and canopy of trees in the North Bay Forest and the cities. We've had so many fires and so much dry weather and so much climate change that it's a very worthwhile endeavor. And there's a lot of details, so pay attention. Before we start, be sure you rename yourself to your first name only, please. And if you're worried about your video being shown, turn it off. Stay muted unless otherwise, and any sort of troublemakers, I'm going to kick them out. Use the chat for questions and answers, and please ask a bunch of questions. Raise your hand if you want to be called on. And let's get started.
Okay, so I'm Jim. I'm with climatechangeeducation.org, and our program is the Mobile Climate Science Labs. We specialize in doing hands-on science at science festivals and large events, which of course we've not been able to do for a bit. Today we're debuting with the remote science festival, our ways of being able to make it as interactive as possible and to be as close to a physical science event experience as we can. So for that, we'll ask you to take advantage of being interactive and ask questions, and you're going to get to direct a lot of the action. Okay. With me today, I'll introduce in a bit. It is Natalie, who's a teacher, and Luca, one of our volunteer students. Adam may be on the call, but we have those folks for sure. And we're going to have a lot of fun today. We're going to start out with some demonstrations, some labs, and then move to how the science that we're looking at is very valuable in terms of how scientists look at tree health. It's in relation to climate change, but certainly on tree health and how forests, and we can learn a lot from satellites and vehicles in the air, planes and helicopters and so on. But this is going to be a lot of how come it works? Why does that work? And how is it important? Okay. I'm going to maybe refer over to Natalie on a little bit of being interactive, how we want to have you have a chance to direct the action, ask questions, and have as much as a conversation as we can.
Hi, everybody. I'm Natalie. I'm a middle school teacher, and I'm really excited to be looking into the chat and seeing your questions or your comments there. We'll have some opportunities for you to make predictions about what you think is going to happen next. We'll have some opportunities for you to ask for specific activities, things that you'd like to see us do. You can direct message me or Luca. Luca's also going to be in the chat speaking up. And you can also raise your hand, and we're happy to unmute you if you raise your hand and wait to be called on. So Luca, over to you.
Actually, I think we're going to start with Jim.
Yeah, did you want to introduce yourself, Luca, or we're ready to go?
Oh, okay, sure. I'm Luca, and I'm a middle school student in Washington, D.C., and I help Natalie and Jim present in these demonstrations, along as some of my fellow students who are not here today, but, you know, they've been in some of the other sessions. So I guess I'll turn it over to Jim now.
Okay. Yeah, so we're going to look at a few things to get to know this invisible light that our eyes are not able to see, and we're going to get to some cool things. We're going to start out with this object, which I think we would describe as a black disc. We'll look at it from a couple cameras. We want you to get an idea how we want this to make this real. So we have a few cameras so you can see things from a few different directions. Okay. And we're going to see what's going on. Now, the way we're going to do is, in this introduction to the other camera, is we are going to be looking at things in two kinds of light. On the left is regular visible light, which we've been looking at. And on the right is an example of this short wave infrared light. Now in science, yeah, go ahead, Natalie.
Jim, I was just going to say, if you are watching Jim move that disc around, you may want to put in the chat what you think it might be, because so far it looks like a round black object, and you might have some ideas about what that could be. Arav says a mirror. Let's get some other ideas out there. That's a really good hypothesis, Arav.
Okay. And in terms of terms, especially for this session, know that scientists sometimes call different things, call the same thing different terms. So there's another term for this particular kind of infrared, and that's called near IR. It's because it's right next to what we can see. So it's very near. So we just want to know those two terms are interchangeable in terms of how we use it. Short wavelength and near IR. We mean it to be the same thing in this case. Okay. So we're going to see mirror or something. Yeah. All right, so let's see. Are you ready? Shall we go? We're gonna see one more time. We'll see it. Here it's invisible light, and let's see what can we see if we look at it in shortwave infrared on the other side. And I think even the time's right. It's a little bit in there. Why? What are we going on here? We're able to, the idea is that with different types of light, we can see things that our eyes can't. There's going to be things are going to look different and they're going to act different. Now, in this case, we have a special filter. It's a kind of black paint that's on the glass or the plastic of the clock that is stopping the light we can see, the visible light from getting through to bounce off the face of the clock and for us to then see it. But it is letting in this short wavelength or near IR, and we can see through it. So this is just a step. We're going to see some different things. I want to show another example. We have to now, as we go on, there'll be more time for you to say things and more we can come back, and there's going to be plenty of time just to mess around today and have some fun. Okay. So I want to look at another thing. If we're going to look at, so I've got a couple of flashlights. Okay. And we're going to see these now. I'm going to take it up to the microphone that's right here, and you can hear me click it on and off. So I'm clicking it on and off, and we're seeing there's going on, but I'm not seeing anything. Maybe I ought to change the batteries. I wonder what's going on. Okay. And let's, though, go ahead and we'll go now over to shortwave infrared. And we see actually that the flashlights are on. Okay. They're just making this shortwave infrared. They are not making visible light. So we can't see any light that's going from them. If I shine it up at the camera, you see it goes very bright on this one. Also on Natalie, this is the way, or so we have this one, you can tiny see a little bit of visible light. It's very close to visible light. This one's far enough away that you really can't see anything at all. So, but here are these two. That's why I have this yellow one tells me that's the right next to what we can see. And this one's far enough that you just really can't see anything at all. Okay. All right. So we're going to be pretty close going over to what Luca's going to be leading on. And I want you to also get a sense, if you hear how Luca does things, I am going to follow along with what Luca says. So later, when you want to have me do something, you do the same thing. You describe something, and I'll do my best to be your hands. You know, I'll be like a robot that does whatever you want. Okay?
Before Luca jumps in, I got a direct message from Anya, who says, if different types of light affect how you see things, how come people use blue light glasses on computers, but the things they see or their sight isn't different? So that's a great question, Anya. When you are looking through the blue light glasses, you're still using your eyes, right? And so your eyes can only see visible light. Even though there's invisible light, infrared light all around you in your room, well, there might be if you have the windows open or the curtains open or whatever, if sunlight's coming in, there's infrared light around you. But since you don't have a camera or something, a piece of technology to help you see that infrared light, the blue light glasses are just changing how you see visible light. They're not changing how you see invisible light because you can't see it without the camera.
And if you don't mind, since this is the last one, I've got some things that we haven't done yet today. So we're gonna go, Luca, if you hold on a minute, I'm gonna do it. I thought I'd just try these out. This is just in case colors or filters comes up a little bit more, is these are just some different filters. So that I'm really not familiar with the blue light glasses and things, but I think this might be the idea. So there's a blue filter. And so it's letting the blue light through in the visible. You see, it doesn't make much difference in the infrared, but here's a yellow filter. Is this of any interest to anybody on things? And here's a red filter. You can see, but this is also good just what is a filter and how we're using it is we mean it as something that lets some types of light through, but blocks or holds or absorbs other type. Okay. And there's other things. And you can see this, these are things that we can mess around with later if we want. We can do some experiments with. Okay. If we're good with that, we'll go ahead to Luca on describing things.
Okay, so I'm going to talk about these cards. You've seen a few of them. They're like regular playing cards. So what is this all about? So let's just look at visible light for a second. And now we have the cards separated into two decks. One is red cards and one is black cards. So let's see both decks. They look pretty normal. This is like a normal deck of cards, maybe one that we would play, you know, I don't know, whatever kind of card games you like to play. But let's see what it looks like. Let's turn them over and let's see what each type of card looks like in infrared light. So let's go to infrared light. Now, let's pick a black card first. That looks kind of normal, right? Now let's try the red. Actually, hold on. First, okay. There's nothing there. That's because in infrared light, colors are things that only exist in visible light. That's what our brains interpret the visible light as colors. But in infrared light, there is no such thing as colors. So when we shine the camera, there's no reds. There's no red. There's no colors at all because there's no such thing as colors in infrared. It's just brightness. So the amount of brightness in the infrared camera, that means if it's really bright, it'll show up white. If it's really dark, it'll show up darker.
Yeah, Luke is exactly right. Like the more infrared light that is passing through or that is reflecting off of something, you're going to see that as bright or whiter. And if something is not allowing infrared to pass through or it's blocking it from reflecting it, then it's going to look dark. You could see that the tablecloth on Jim's table looks black under visible light, and it looks sort of whiter or light gray on the infrared camera.
Okay, so I'm going to go with cues you're getting from that. And now, do we cover that if we would like, if you would like, and if it's working, that some of the kids that are on the call, or students, however you'd like to call yourself, but the younger people, if you'd like a few folks to unmute themselves, we'd like to hear from you. And also you're reacting and you're able to ask questions that way. If you'd like, you could raise your hand or write in the chat. Yeah, I'd like to speak up. Is that working okay, Natalie? Or is there a reason we can, can
yeah,
we do that?
No, there's actually a lot going on in the chat. So Naz has chatted. She's like, I understand only lightness and darkness. Good explanation, Luca. And people are saying, why don't magicians use this? But a lot of times we're answering also in the chat so that we can keep the flow of the experiments going.
Okay. So in any case, to do that, so what I'm looking for is do we want to stay a little bit longer with this, or we can start going over to how this science, it's fun, it is like magic, but it's also science, how this is used to study how forests and plants and agriculture is doing, especially lots of it from either in space or from up in plains. Okay.
Jim, just a suggestion, maybe we could, I know it's a little early, but maybe we could try the poll, like if we want to know what people want to do.
Yeah, okay, it's up to you.
So Anya says, so these are not special types of cards. And that is correct. This is just playing cards like you could get at any store. They sell them at grocery stores and other stores, just like what you would play with your family. And then like Sana and said she or they want to know how the clock thing works again. So could we go back to the clock, Jim, for just a second?
That's right. Now these cards are a little bigger because they're more fun, and we actually use an even bigger one. But one is where it is true. These are just regular cards, and you'll see more things that'll convince you of that. But we like if you ever that is fine if you ever say, you know, I want a little proof of that. I think you might be tricking me, or give me a little more. That's okay in science. We need to show proof. We need evidence of things. Okay, we don't mind that as long as people pay attention when the evidence says something's true. That part scientists aren't happy with. If someone, no matter what you tell them, they say, I don't want to believe anything. Okay. This thing, I'm going to use this with a combination with another way in which we have this same filtering material. Very soon you'll see that although this is a product that is sold for security reasons, it is not unusual in nature. In nature, what we're talking about is actually very common and very important to plants. So it's a special paint that we've now used on some just acrylic paint sheets, right? That have this property of blocking visible light on the left and letting invisible light through. So essentially, what you're seeing now moving around this material, that's been spray painted onto just a regular clock. It's just a ordinary clock. We like to use things that aren't tricks. They aren't expensive. They're very normal. And so this is this filter. And we're going to see lots of filters today. We're going to do this one. How are we working on this? Now we can actually even see some filters that do the opposite, that let visible light through, but stop the shortwave infrared. Okay. Does it help by seeing this, that here I'm doing this? So like if, another way to put it is if I put this card, I can't see the card anymore because I put the filter in front of it, but I still can see it through the shortwave infrared. Okay, that's all that's going on in the clock, and we like things to be fun, and that's meant to be kind of a surprise. Okay.
Jim, Nick said, do they use filters in dark rooms? I haven't done any photography, so I'm not really sure. They use filters on cameras, and that's something that we can go into.
Right, and that's it's an interesting one because dark rooms. You tell me if I'm wrong. But dark rooms used to be something we all yet dealt with because we made things with film all the time. And yes, people still make things with film, but they make it now with digital. I don't know. I'm not trying to be an expert on this, but a lot of times you'll see old movies of like people in a dark room and they'll have red light on. It's if they're working in black and white cameras, if they were just making monochrome, that red wouldn't change the film, and that's why they could do it. So you could walk around and see it, and it wouldn't change your photograph. So in a sense, that's a filter. In that the film itself was a filter. It wasn't. It was not reacting to the red light, but it did to the yellow, green, and orange, and blue.
And then I think a good segue. Anya asked, "How come the tablecloth is black under visible light, and it's much lighter? Why doesn't it just stay dark?" And I think you were going to talk about plants, and so maybe if you wanted to bring out the chlorophyll and the plant explanation. And Anya, if you can hang on, this is kind of a longer explanation, but it will all make sense to you in a second.
But Anya, thank you for that observation. Is the idea. That's a lot of it, and it's a very significant observation. It's not just a little side or a quirky little thing. That fabrics, cloth, including tablecloths or a shirt, this is a very common characteristic that they'll have, and it's very surprising. You're thinking you're wearing black pants, but in this light, they're very bright. Okay. Well, what I want to do is go right to something, and then we can see other things with this. This gets right to the one. There's a characteristic about plants that of course, generally use chlorophyll. At least the leaves do. That have a very special property. That's just one, it's very cool and interesting, but it's also, I'm getting something down, so if you hear me moving a little bit, but it's also allows scientists and us to tell where plants are and how healthy they are. Okay. And let me see, this is the first time we do this today, so we have this one. That is a white background. This is some carrot tops. This is some carrots we got from our local farm recently, and what do people see?
Would anyone like to unmute themselves and make some observations? Go ahead, Nick. I see you're unmuted.
Meanwhile, I'm putting down some other leaves.
White.
Yeah.
That's right.
I mean, isn't that kind of amazing? I mean, it's, and we'll see pictures from the air of trees and things and how, so it looks fairly dark. Red is really, really dark. And what we see is some green coming back, but boy, do we see a lot of shortwave or near IR coming from it. Okay.
I think Tyson might have wanted to say something. Tyson, you can unmute yourself again if you want.
Okay.
What did you want to say, Tyson?
It looks white. It's harder to see the carrot top bands on
True.
or the parsley or whatever that is
Mhm.
on the infrared than the other one.
Those are good observations. And Jim was talking before about chlorophyll. You probably already know chlorophyll is the part of the plant that makes energy from sunlight. There's a funny joke. What happened to those plants? A frost? Very funny.
Here, this is a bird of paradise. I just want to get an example of a really big leaf. So this is from my backyard of a bird of paradise. And you'll see, so you can see it happens pretty much all the time. A nice, healthy green plant tree. And poor guy cut it off this today, but this, you can see how it has this characteristic. So I'll tell you what. Now, Natalie, you tell me where we go. We can take a. No, this is one of, if you don't mind, Natalie, on this one, I'm going to hold a little bit on what you're referring to is we can take a look at liquids, including chlorophyll. But I'm going to lead into that for a second, okay? On that
Go
one?
ahead.
Okay. So let's just see. We'll get some ideas of where are we? Okay, we're going to go over here for a second. And okay, this is something from the air, and people can see how well, but this happens to be San Diego. But as we go down here, take a look. What we're going to see, instead of split screen, we're going to go from shortwave infrared to visible back and forth. And right as you come into the airport in San Diego, it goes over a lot of trees. And take a look at how different the trees look compared to how they look in visible light, okay?
Oh yeah, I can see that those are tall palm trees. Yeah, Nick says it looks like it snowed.
So that's really it on that one. We have some other from the Bay Area a little bit, but just an idea of how that gives us just an idea of how that how we can see things from far. You can see a lot of trees. This ability allows you to identify and notice a lot of trees, not just a few in front of them. Okay. Later we can start this guy up, but that's we're going to have some different examples of it.
Jim, Anya asked, what if it was a Venus flytrap? And I wrote back, I think it would still look light, because even though Venus flytrap, eats protein, like eats animals, it's still green. So it's got to have some chlorophyll in there. And it's the chlorophyll that's making it, look that bright color.
And then I think now I don't want to spend too much time on the videos, but know this one is you happen to ask something. One video that we have here, the one that's not playing, but it's there, is actually a video about a Venus flytrap. That's part of it. So
at some point, Anya would love to see that, I think, because she asked specifically.
Oops, I just messed it up. Let's see. Here we go. So I'll tell you what, we'll play it a little bit. I don't know if she's got it right now. This was at another science festival that we were with in Washington, D.C. And anyway, she's about to show people. Anyway, you can see some here, and let's see if I think in a minute she's going to pick up one. Can people see that right now? Is that coming through okay?
Yeah, we can see the plants. Yep, it's
okay.
Split screen.
It's not as interesting, but you'll know. Okay, there it is.
Oh, there's the Venus flytrap. Are we going to see it in split screen? Oh, there it is.
Picture plants.
And that's what she's talking
Yeah,
about.
I think somebody made the observation that this is actually, I think this is a pitcher plant, but it's.
Oh.
You're right. Yeah,
But-
you're right. And I'm sorry that was a little misleading on my part. But I think they're similar enough that it's not too off. You tell me if it's wrong.
Yeah, they're
Right.
very similar. They're just a little bit different. The pitcher plant is a little bit bigger.
And thank you for correcting me. I don't mean to be wrong. I don't mean to give wrong information.
It still eats meat though, and that was kind of the point of the question.
They
Yeah.
can eat your fingers, someone commented. Got to be pretty careful with those pitcher plants. Oh, so remember the original question was, why does the tablecloth look dark under the visible light and light under infrared light? And it really relates back to this property of the plants.
Yeah. And let's see if I have it, if I'm back up here, we'll come into back to visible. So in a bit, what we can do is we can look at different fabrics, okay, different plant things. But what I would go with is if we've seen that all these different plants have this characteristic, like the tablecloth, they look pretty dark or really dark in visible light, but they look really light. How people color or dye, the coloring that they use to make fabric the colors we want, use different types of material. A lot of it is based on chemicals that are taken out of plants. And when they are, you tend to get this property that you have clothes that look light in shortwave infrared, but dark in visible light. Others that use the same type of material that say that they color tires with, or a lot of plastics with, that's something that's carbon based, and that doesn't have that property. I didn't want to bring a car tire. That'd be kind of not very fun, but this is a bicycle inner tube. And you can see it almost even looks, I think it even looks darker if you see what I'm saying, it's kind of folded up. And I think it even looks darker in shortwave infrared than it does in visible light. At least it's not as reflective. So that's an example that colors a lot of things. It has this stuff called carbon black. It is like charcoal. It's a term for a special kind of dye or coloring.
So the dye that makes the tire black doesn't come from plants. It comes from carbon.
Yeah. Yep. And it's a thing that a lot of people have never heard the term carbon black, but boy, is it used a lot in black paint and black plastic. It's used for a couple reasons and for tires. Why? Tires are made of rubber, which naturally is actually a very light color like this. It's light, but they put the carbon into it.
Let's ask the group, let's ask the kids, can they see anything else on the screen that's made with carbon black? So it appears black both under visible light and under infrared light.
The rim of the clock?
Yes, you're right. I'm not sure who said it, but that was exactly right. You were noticing that. And also the back of the cards, maybe. I don't know, the cards. What do you think, Jim?
Flip them up
Yeah.
so that the thingy is the.
So you can see the face?
The black, yeah, the face of the card, the black face.
Yeah, I'm gonna be pretty confident that they're using a dye that used carbon black. It is used so much, and it works, and it's effective. Now it just happens where when they make it, I don't think they're thinking too much about how it looks in shortwave infrared. But carbon black just absorbs so many kinds of light. It just goes straight all the way into near in shortwave infrared. But yet we see some that are some way, some another. Let's see.
It's about 5:30, Jim.
Yeah.
It is
okay.
exactly
maybe we should do
5:30.
the poll now.
Okay. I'm gonna while you're doing that, I'm gonna just bring up one other thing here. So this is, let's see if I should put a white background as, but usually, yeah, my wife has been very nice today that she let me kind of raid the kitchen for a little bit. Here's a pomegranate. Where am I going here that I've got the
You're
wrong
good
light?
on the pomegranate.
Yeah, and these are blackberries and blueberries.
Yeah, that's impressive, the blackberries and blueberries.
And I was a little surprised. I thought the brown, this is a banana we're putting in the freezer. I mean, it's kind of gone, but if we freeze it, we can make a smoothie out of it, but it's still light even in shortwave infrared. That kind of, so you can see when, and here's a carrot, baby carrot. So, I mean, it's pretty much in plants. And by the way, Natalie, we were talking about that animals don't see near infrared. We don't, they don't. It doesn't look like there's much of an evolutionary reason to see. Everything looks kind of the same out in a forest or somewhere. So maybe, there's not much advantage to be able to see near infrared if you're just living
There are
out in the wild.
animals, just to know, there's a few animals who see in a different kind of infrared called long wave infrared, but we can talk about that later if we talk about long wave infrared.
Yep. Okay, so I'm gonna get
most notably rattlesnakes.
Yep, I want to get to some of the things how scientists use this, but I do have another video queued up a second of just I'll just play this for about a minute or so that we can see some other familiar places in near infrared. Okay, so this we're going to get up to the North Bay in a minute, or at least Marin County, but we're going to start out it starts out with San Francisco, but you can see the different areas. As you'll see, there's another characteristic that water tends to look a lot darker in shortwave infrared. This particular angle, you don't see it so much, but now here we go so we're going to North Bay now, and you can see how things look from the sky of in near infrared.
So just a second, while we're watching this, Arav asked if we can't see this, how are we seeing it on a camera? And Lucas said, well, there's a special filter, and he's exactly right. And then I said that the filter helps the camera to measure how much infrared light is passing through. If it's like 100% infrared light coming through, it shows us a bright white picture. If it's 0% infrared light coming through, it shows us a dark picture, and everything in between is some sort of shade of gray. So you're seeing how much, like in number of photons, is how much infrared is passing into the camera lens. So it's really a number. It's a number. It's an amount of infrared that is out there in the world. And the camera is changing that number into a shade that's somewhere between white and black.
Okay, so let's, I will now go to, so these are some images of how this technique is used. There's a term you don't really, it's kind of like DNA. You don't really have to know how to pronounce all the word to know kind of what it's about. So there's this term NVDI, and I can go into it, but I'm not saying you have to know what the word means. But you can kind of recognize it. It's a term that they use a lot of how they use a balance. We'll describe how it works to tell where plants are and are they healthy or are they not so healthy. Now, I'll try and catch up with the pictures that are being shown a bit, but okay, let's see if we can stop there for a minute. That one is, I know it's kind of hard on the screen a little bit. Oops, darn, I thought I stopped it. Anyway, okay, well, wait till it comes back a little bit. I'm sorry. That what they're able to do is, and of course that uses computers. Computers can look really quickly, and it measures how much red light there is, the part that chlorophyll absorbs. That's where the chemistry goes on. The taking energy from the sun is the red light, of how much things are red and how much things are in this near infrared, and then they compare the two. If there's a lot of red and not a lot of shortwave infrared, then it's probably water. It's probably like the lake that's here. And they put a red on it. If there is a lot of shortwave infrared, it's very bright, but not a lot of red, that's probably going to be a plant that's going on. If it's somewhere in the middle, if it's pretty even, it could be a lot of things, including it could be a plant that's not very healthy. Yep. Mm-hmm.
There's a question. Well, there's a question in the chat. So Arav says heat camera, and it's actually not heat. It's something called false colors, and I was wondering if you could explain that.
Right. Now, that was a good observation because that certainly looks like a thermal image camera. And maybe that's an idea of the question was that before, that cameras these days that are tied to computers take information, maybe we can see it, maybe we can't see it, and then run it through the computer and say, well, let's make it so people can understand it better. And so if we want them to see it better or we want to see it different, we'll put a color on something based on, as Natalie said, the numbers, the information that we have, and we do it. And that's used a lot in thermal cameras, right? Thermal cameras take other kinds of light we can't see, and they make one color if it's really bright, another color if it's medium bright, another color if it's not bright at all, to help us see colors we can't see. In this case, they've used that same technique of saying everything that is yellow, or everything that's sort of in the middle, make it yellow. Everything that is really, really more like a plant, will make it red. And everything that is more like water and the other will make black. Okay, so that's where they use that technique. But we can look at thermal camera images a little bit too. We got those, but let's see if I'm not using the machine right. Is what's going on. There we are. So that's an idea of satellite images looking at a whole like a farm, a big farm area, and they can say where I believe it's where the green is. Those are healthy plants, and the red is those. That's part of it's not doing so well. I think I've got that right, but they look at the different colors and can tell, and you can get an idea. They can look at the areas, large areas. I mean, and this no satellite did this all at once. This is a whole bunch of pictures all put together, but the idea of you can tell where it's that they use this technique of using shortwave infrared to map out where in the United States is it greenest at this time of year. There's a whole bunch of satellites that do it. One is known as Landsat, Landsat. That's been around for a long time. There's a whole bunch of Landsats. They used to be way back in the 1950s, I think in the 60s, and now we have Landsat 8, and they still make those techniques, but there's a lot of satellites to do that.
So they have a fancy satellite with a fancy camera, and instead of showing the plants as bright white like our camera does, they have their camera programmed to show the plants as bright green in that picture of the United States, and to show things like sand and whatever as brown. And so they have just set the camera colors to show different amounts of infrared light as green or brown.
Right. Exactly. Now, again, we don't know if we have to get too deep into it, but what this is trying to say is how this technique works is when you have a green plant on the left that's healthy, what that really saying is it reflects a lot of the shortwave infrared and it absorbs a lot of red light. That's what's going on. In a not very healthy plant, it doesn't reflect as much near infrared, but more importantly, it's reflecting a lot more red because the chlorophyll is not working very well. I want to see if I get an example here of how that kind of works. I have some leaves here.
Yeah, Nick wants to know what a dead plant would look like, or a not healthy plant one.
Yeah. So there's some leaves I just gathered out from the backyard, and you can see, the common, they tend to look brown, right? They look lighter. The chlorophyll is gone. Or is no longer chlorophyll. It's broken up. It's like in the winter deciduous trees, the ones that leaves the leaves, the chlorophyll goes back in the plant and they save it. So it looks kind of brown. It doesn't have that greenish look to it. Now we can kind of do that with our eyes, but the computers with the cameras can do it very fast and say that look of red, pretty reflective, and shortwave infrared about the same, that's not a healthy plant. But if we contrast it to wherever I put any of these guys, we can see just how different that looks. Right?
Yeah, to the kids, it's looking pretty similar. I'm wondering if you can explain the difference.
Yeah. Well, would you say? I mean, we look at the infrared part; it looks pretty similar. That's not much different. They're both very light, right? But let's see this. now I don't know if I'm ready to get really fancy here. While maybe these are, if we might say which one's darker, I don't know. I would say the dead leaf is a little bit lighter, but not super, they're both not, they're sort of in the same range. But the dead leaf, there's a lot of red reflecting. Brown, when you see something brown, it actually is dominated by red, where this guy is a lot of green, but not very much red at all. And that's what the computers, they look for. They're looking specifically at red. They're not looking so much at green.
Oh, and so they're just using a different band of infrared than the camera that you have turned on right now. Like they're looking at their camera is slightly different than the one that we're looking through.
Well, actually, no. Our camera and what they use is very similar. And what I'm saying is, it's the ratio. It's the compare. Which one is more compared to the other? They expect that if you're looking at two plants, right? They expect that the near infrared will look not too different between dead and alive.
Hmm.
But if now they think that's a plant, now let's look at the red. If there's a lot of red coming back too, then it's probably a not live plant. And this guy, if we put a red filter, and sorry, I didn't bring things for red filters right now. While this is nice and bright green, it's not reflecting very much red light. I do even have red flashlights and all kinds of stuff, but I didn't really do it on that. So that's it. It's a tricky thing. And I'm going to say it's not very, it doesn't jump out at you, but that's why the computers are good. They're tuned to look for that little difference. Now, maybe we compare it to, I realize when I see this, it's not as dramatic as we saw these cards, right? That was dramatic. That was very clear. It's kind of subtle, but they use it a lot. This is potting soil, and you can see it's a little bit lighter in the shortwave infrared. But that's an idea of when the satellites go over, they say, no, that's just dirt, that's just soil, or that's asphalt. Asphalt is black in both of them. That's all they do. Their job is to look for these little differences. We would get tired flying over and looking for all trees everywhere. But they can say, this looks like a green plant, and that looks like another one. The idea is another broad one is people's use of shortwave or near infrared has really taken off in science. It's being used in a lot of areas around climate change, around plastics, around all kinds of stuff. But among them is this quick way of doing plants. I did a lot of talking, too much talking there. Sorry about that. Let's see. I have another one for you. Let's see if I can get this up.
Jim, we're at 5:43, just to keep you alert
good.
to the time.
Okay. If we do a little brief one of this is by comparison of, so this is actually from a satellite, the one that we like use a lot, GOES. And it's to get an idea that the shortwave infrared, this is looking at Houston, but you can see another characteristic this stuff has is it really is good at being able to tell you where water is. You'll notice, you can't necessarily see all these lakes and ponds in Houston, but when you look through the shortwave infrared, it's pretty easy to see. So that's another thing they look at is okay, they want to know, they look at the moisture in plants. Some of this stuff is pretty tricky because they've really gotten good at it. That one that looks like kind of like a flag, I think that one looks really cool. And this is landing. But you can see the same idea that the vegetation, the plants, the trees, they look much brighter.
Jim, did you want to show the liquid chlorophyll?
Right. You've been patient with me, Natalie. I will do that.
And some of the other liquid materials.
Yeah. Thank you. Okay, so let's set that one up. What have I done with the whiteboard? Okay, we're going to get to, I'm going to first do the fun part and then get to how this is relevant on some of this here is, okay, well, one of the things I had is that this ability to see through things in shortwave infrared where, let me see if I can get this a little brighter too. I'm going to see if I brighten up. It's not as bright as I would think it would be. Come on. Yeah, it's a little brighter. Okay, the ability to see through things in shortwave infrared, but not in visible light is, yeah, there's a special filter, but this is just coffee. This is regular coffee. And does that look on it? Now, other things that are very good at this is grape juice or wine. There's other things that do that. Okay.
Jim, if you write on the whiteboard, maybe we can see through the coffee in infrared.
Yep. Right. Mess up my pen here. Boy,
we're not worried about spelling. I have no idea.
I made the same mistake in the chat.
It's funny, you know, when I got my mind on things that I do know how to spell. Right now, I don't know how to spell. So, if we we're doing this now, if we I'm going to do one that we tried for the first time. So Natalie and Luca know the answer to this one, but this is one just meant to say not everything does it. This is orange juice, and what we thought was, and this is when we can get into. This is actually relates to plants. Is this has a lot of plant cells in it. Orange juice isn't like wine or grape juice where it's very liquidy. It actually has little pieces of it, and that's part of that's actually why the plants actually look very bright. You know what? It's this combination. So it's this thing. Yeah. So the thing is, if we look at a plant and we say, and we get it that plants look very bright in this, we're looking at chlorophyll. Is it that the chlorophyll is reflective? Is the chlorophyll the reason it does it? Or is the chlorophyll got another property to it that something else is going on? Why do plants look so bright? Can you think of an experiment we can do to tell what is it about chlorophyll that makes this happen? Okay. And I'm going to lead right into it. I've got some chlorophyll here for you. Okay. This is liquid chlorophyll. Yeah. So here's some liquid chlorophyll. And, you know, I think I've got my shortwave light in some funny angle. I don't know why I'm having trouble with that a little bit, but if we go with this way, so we can see right through this, and I'm not sure what have I done to my lights here that it's not as dramatic as it want, but you certainly, well, we know we're not going to see through this, but can people see that the chlorophyll is almost transparent in the shortwave infrared. So the idea is, I have a picture. I have to get it, but I'm going to draw it on here just for a minute, and do it this way. Is if we have a plant, there's a layer where the chlorophyll is. Okay, that's where it goes. A lot of that's going on, but underneath it are a bunch of cells that are kind of like skin cells. And cells are maybe not circular, but they're roundish. Okay, and they're sitting underneath. When we have the sunlight come in, the red in the sunlight really gets absorbed by the chlorophyll. It loves it. The green is pretty reflective. It mostly reflects back out. Okay. The shortwave infrared goes right through the chlorophyll. Okay. It's not that the chlorophyll makes it bounce out like it does green. It reflects green, but the chlorophyll, it goes right through. And when light goes into kind of like soap bubbles or cells, what happens is every time they hit a change from air or, you know, one type of material from another, they reflect off of that little piece. So I'm saying is every time they hit the outside, a little bit reflects here. Every time they sit here, it reflects here. So it ends up scattering the light all over the place. And the result is the plant is very bright. The sunlight that comes in, bounces around, scatters, and goes out in all directions, where the red gets absorbed and makes the chemistry happen, makes the energy stuff go on.
Yeah. we have a few questions in the chat. One is one of our guests would like to see the difference between the black suit and the red suit cards again because his sister his or her, I'm not sure, his sister wants to see it. From nick.py, isn't the chlorophyll inside cells?
Yeah, and I'm not going to pretend where I'm an expert, where I'm not. I think it's this. So tell me if I got it wrong. I think there's certain types of cells that are up here that where the chlorophyll is. I mean, I don't think I don't think it's just like this sloshy little area up here, but there are ways in which the plant is holding on to up here, but there's other types of cells that say are more the fiber that hold on that are underneath. And for instance, like when the plant dies or loses its chlorophyll, well, it's still a plant. I mean, it doesn't just disappear. Those cells aren't gone. So I think it's something along that line. There's a layer, let's say there's a layer where there is chlorophyll, where this happens, and there are these layers underneath that allow it to bounce around and scatter. Okay?
We got 4 minutes, Jim.
Yeah. So
Can you show the cards again, because we definitely want to see
okay.
them.
So the person wants to show his sister. I'm sorry if I'm getting that wrong, but if you did,
Yep.
do you
Son.
want to describe what happens and make it a surprise for her, or do you want me just to show it?
Son, do you want to unmute yourself and tell your sister what to expect, or talk to your sister?
Yeah, I told her a little bit what to expect, but I like you to show it so I can explain it to her.
Okay, go ahead. Just explain it with your microphone
you
on.
explain it, and I'll follow along like I did with Luca.
Okay, so basically the infrared basically kind of sees in black and white, so color doesn't really matter to it. So when you show the black suited card face up.
Oh, I did the wrong side. I messed it up. Sorry. I got a red card in with the wrong one. There we are. Okay.
So it shows the black suit, but when you turn over the red card, since color doesn't really matter to it, the color shows up as not there or invisible.
Well done, Son. Very nicely explained. Oh, so I forgot to let everybody know, if you are interested in this and want to talk more about it, you can write to us at our email account, which is write us at climatechangeeducation.org. I'm putting it in the chat right now. And you can also visit us on YouTube. So we've got 3 different YouTube channels. One is Climate Club DC. One is Mobile Climate Science Labs, which I'm spelling out right now, Science Labs. And the last one is Climate Change Education. So if you look up us under any of those names on YouTube, you'll see a lot of videos where Jim or the kids are showing you cool things with long wave infrared or short wave infrared. Yeah, we also have Twitter accounts for all of those too. So if you or your family's on Twitter, you can check us out there.
And normally if we're at a science festival, we get people who sign up who want to be our volunteers and say, we do things at other events, we do things for schools, and we're all volunteers. We just believe in doing good science and making it fun. We're transitioning until the pandemic's over, and then afterwards we're going to learn from this is how we can share it remotely, but it's still in an interactive way. But just know, if you like some of these things, we're always looking to work with other people, even whatever amount they're interested in. Okay, and we also can share.
And I got to say, it's tremendously interesting stuff. So if you don't volunteer, you're missing out on something. I'll tell you, science is exciting, and you've proved it today. Thank you very much. Thank you, everybody that's attended. This is the end of our Science Discovery Day. We will be back. I'll guarantee you, we will be back.
Thanks, everybody. Bye.
Everybody say bye. I'm going to close it in 10 seconds.
Thank you,
Bye.
everybody.
Bye.
Thank you, Don.
You.
Thank you. Bye-bye.
Bye-bye.